All right, let's get going on chapter 3. So chapter 3, we're going to start by talking about some of the early discoveries in chemistry. So the ideas that form the foundations of chemistry started way back before the birth of Christ, 400 BC, with a Greek philosopher named Democritus. And he was the first person recorded to come up with the idea of the atom being a basic building block of everything around us. And then a whole lot of time went by. Alchemists, you might have seen movies or heard stories about famous alchemists trying to figure out how to transform lead into gold. And they were kind of the early chemists. They were doing things with chemicals and chemical reactions, but they didn't really understand or really try to probe deeply into what was actually happening. And it wasn't until the 1700s where Antoine Lavoisier was a French aristocrat who had a lot of time on his hands, and you'll find that a lot of the more important things that we talk about as far as scientific discoveries are, arrived at by people that have lots of money and not much else to do with their time. But Antoine Lavoisier came up with the idea of the law of conservation of mass. And why this is important is that in a chemical reaction, matter is neither created nor destroyed. And how we sort of think about that in chemistry is that the mass of whatever you start with in a chemical reaction, your mass of your reactants, will always equal the total mass of your products. And then our next one was John Dalton, our next sort of important guy. And he came up with the first atomic theory. And those important parts of that are that elements are composed of atoms. So the simplest possible version of an element is an atom. The atoms of each element are unique. So the atoms of carbon are unique to carbon. They're different from atoms of oxygen or atoms of hydrogen or any other atom. Atoms combine in fixed ratios to form compounds. So for example, a molecule of water, a compound made up of hydrogen and oxygen, will always come together with 2 hydrogens and 1 oxygen. We never find 4 hydrogens and 1 oxygen or 1 hydrogen and 2 oxygens. It's always the same. If you have water, it's always H2O, 2 hydrogens, 1 oxygen. And then atoms are not changed in chemical reactions. So what that means is that in a chemical reaction, atoms can move around, but the atoms themselves are unaltered. Okay, they can trade partners, they can go somewhere else, but the atoms themselves remain intact. So let's take a look at a pictorial description of the law of conservation of mass. And remember, that idea is that the amount that you start with in the reactants on the left-hand side has to be the same as the stuff on the right-hand side. Things can move around, they can trade partners, but whatever I start with on the left, I have to end up with on the right. So looking at that first picture for A, on the left-hand side, I have a total of 4 blue spheres. On the right-hand side, I also have 4 blue spheres. On the left-hand side, I have 2, 4, 6, 8 white spheres. And on the right-hand side, I have 8 white spheres. So everything is the same on both sides. The same number and type of things are on both sides. Same thing for B. I have 2 blue spheres on both sides. I have 2, 4, 6, 8, 10. 2, 4, and 6 makes 10, so the same of everything on both sides. And then in C, I have 4 blue spheres on the left and only 3 blue spheres on the right. So my mass has not been conserved. I've lost one of those blue spheres. So C is the one that does not follow the law of conservation of mass. Let's take another look here. So for line A, on the top there, we have 1, 2, 3, 4 orange spheres. And on the right hand, we have 1, 2, 3 orange spheres. So right away, that first one I don't have the same mass on the right as I do on the left, so A does not follow the law of conservation of mass. All right, so question 3. So before you try to do question 3, I'm going to write a chemical equation for you. So in this example, it says that zinc reacts with hydrochloric acid and produces hydrogen gas and zinc chloride. And so I can write an equation for that looks like this. I'll have zinc, Zn, plus HCl, hydrochloric acid, makes zinc chloride and hydrogen gas. I need 2 here. Okay, so it says that 65.4 grams of zinc and 72.9 grams of hydrochloric acid react. And then they produce 2 grams of hydrogen gas. How many grams of zinc chloride will form? So the law of conservation of mass, we have the mass on the left has to equal the mass on the right. So on the left-hand side, we have a total of 138.3 grams of material. Okay, total mass of my reactants is 138.3. The total mass of my products also has to be 138.3 grams. So if 2 grams come from the hydrogen, then that means that the zinc chloride has to equal 136.3 grams. Okay. So now, getting away from the math a little bit, which I'm sure many of you are going to be breathing a sigh of relief, we're going to talk about the periodic table. Now, the periodic table, I want to make it clear, I do not expect you to memorize the entire periodic table. I've been doing chemistry myself for over a decade, and I don't have the periodic table memorized. I know most of it, but I don't have it memorized entirely, so I don't expect any of you to either. There is a list in that document that I've shown you on Canvas where it describes what elements you need to be able to recognize, but that's about it. So, but we will expect you to understand what are the different parts of the periodic table. Okay, so you'll notice right away we have this this lovely legend, and the bluish sort of periwinkle colors are the metals. The green ones are the nonmetals, and then along that sort of stair step between the metals and nonmetals are what we call metalloids. Okay, so they're elements that have properties that are similar to both metals and nonmetals. Okay, but you'll find that the entire, almost 2/3 of the periodic table is all metals. Now, we can also sort of break things into smaller categories. So I'm going to zoom in here. And that group, so let's back up a little bit. Actually, I just thought of something. So the vertical columns, we call those groups. Groups or families. Okay, so group 1A, group 2A, group 3A, group 4A, 5A, 6A, 7A, and 8A. Okay, and then the horizontals, horizontal rows, we call those periods. Right, so period 2, period 3 through 7. Right. Now I can, certain groups, certain vertical groups have names themselves. So group 1A are called the alkali metals. Alkali metals. Right, that's group 1A. Group 2A are called the alkali earth metals. Right, that's group 2A. Now this large group in between, this whole big rectangular block, these are called the transition metals. And groups 3 through 6 have names, but they're fairly obscure, and we don't expect you to know them. The next group that we do expect you to remember is group 7A. These are called the halogens. Right, that's group 7A. And then the last group is the final one, group 8A. These are called the noble gases. Right, we're talking about the entire vertical column. So when I'm referring to the noble gases, I'm talking about helium all the way down to really just to radon. This OG is a man-made chemical. But helium through radon, those are the noble gases. The halogens are all of these fluorine through iodine. Right? The alkali metals is lithium through francium, that entire column. The earth metals is beryllium all the way down to radon. And so all of the transition metals, this entire group, right? Now this part down below that says lanthanide and actinide series, they actually live as part of the transition metals. They actually live right there on the periodic table. The reason that they're down below like this, partly, is to make the periodic table fit on a normal sheet of paper, to be completely honest. But additionally, the lanthanides and actinides have slightly different chemical behavior that is common through their particular group, okay, their particular period. So, periodic table, as we go through this semester, I hope that you start to see the amazing organization that is inherent in this thing. The more you learn, the more fascinated I hope you'll become with the layers of organization that are in the periodic table. Because it's more than just symbols and numbers. It tells us all kinds of things about what kind of ions things form, how things share electrons or transfer electrons. It tells us so much. Now, the other thing to understand is that within a particular vertical group, say for example the alkali metals, everybody in that vertical group has similar chemical characteristics. So all of the alkali metals react very strongly to water. They explode with water. Okay? So if you ever want to have a good time, if you have the means to get yourself a block of pure sodium, not sodium chloride, but pure sodium metal, chuck it in a big body of water and see what happens. I think you'll find that it explodes rather remarkably. And the YouTube has all sorts of videos out there. If you want to just Google or search YouTube for alkali metals reacting with water, you're going to see all kinds of fun things. But that's because lithium, sodium, potassium, rubidium, cesium, francium, all of those react very strongly to water. The alkali earth metals are similar. Beryllium, magnesium, calcium, they all have similar behaviors chemically. Right? The transition metals are kind of weird, and you'll hear me periodically refer to those as the wasteland of weirdness, because the transition metals, they're just strange. Not a whole lot of patterns in the transition metals. And then the halogens, looking over here at group 7A, the halogens also all have very similar chemical characteristics. The noble gases, you guessed it, all have similar chemical characteristics in that they don't react with anything. Okay, so the noble gases don't react with other chemicals or other elements. All right, it's part of the reason that we call them noble gases. All right, so here's your first little bit of a quiz. So the group 2A elements are called what? Let's come back up. So here's our group 2A on the left, and they are the alkali earth metals. Or alkaline. I've heard it said both ways. Okay, in an effort to keep our videos relatively short, I'm going to go ahead and stop this video here. We will pick it up with our next video on question 5.